Hey everyone, welcome back. Today we're diving into the complex physics and hidden chaos inside an ancient stellar metropolis known as Caldwell 93, or the Great Peacock Cluster. Located a staggering 13,000 light-years away from us in the southern constellation of Pavo, this globular cluster is just a totally fascinating paradox of age, beauty, and absolute cosmic violence.
When you just look at it from a distance, it looks so peaceful, right? Just a glowing, serene sphere of ancient stars. But, as we're going to see in this explainer, this beautiful facade is actually hiding a hyper-dense, chaotic reality that completely pushes the limits of stellar physics.
Here's the roadmap for today. We're going to meet the cluster, check out its ancient stars, zoom way into its collapsed core, hunt for some stellar vampires, investigate a gamma-ray mystery, and finally look at what the future holds.
Let's jump right in. Section 1. Meet the Great Peacock Cluster. Basic stats and discovery. Let's get the lay of the land here. Also officially cataloged as NGC 6752, this cluster is a true relic. Found way back on June 30th, 1826 by Scottish astronomer James Dunlop, it's an incredibly valuable tracer of our galaxy's early history. Because it sits 13,000 light-years away and formed in the early days of the universe, it basically acts as a pristine time capsule for chemical enrichment in the Milky Way.
And this number really puts its scale into perspective. 12.5 billion. That is the cluster's age in years. Let that sink in for a second. That is nearly the age of the universe itself. With all that time, the hundreds of thousands of stars packed inside have had a very long runway to interact, evolve, and fundamentally alter each other.
Section 2. Generations of ancient stars and their distinct subpopulations. Okay, here's where things get really puzzling. If these stars all formed together billions of years ago, why on earth are their chemical makeups so completely different? When we measure the intensity of their light, we see this cluster isn't just one big happy homogeneous family. It actually hosts three distinct stellar populations, populations A, B, and C. Now, population A looks totally normal, just like standard galactic field stars. But the second generations, populations B and C, they are chemically bizarre. They're heavily depleted in carbon and oxygen, yet strangely packed with helium, nitrogen, aluminum, and sodium.
And to make things even weirder, check out how they physically move. The first generation of stars actually rotates faster than the second generation. That is totally counterintuitive to standard models of cluster formation. You'd expect the exact opposite. What this highly unusual structural kinematic coupling suggests is that, despite hanging out together for 12.5 billion years, these ancient stellar populations still haven't fully mixed.
Moving on to Section 3, the collapsed cluster core. Let's do a macro to micro zoom in.
To really understand what's happening at the center, we need to define core collapse. Caldwell 93 is what we call a post-core collapse cluster. Over billions of years, dynamical friction and gravity basically caused the heaviest stars to sink right to the center. It pulled everything into this hyperdense state, creating an ultra-compact city center where stars practically brush past one another in extreme stellar traffic.
Notice that tiny white dashed circle right in the middle. That marks the cluster's core radius, and it's a minuscule 0.17 arc-minutes. When you compare that to the much wider red dashed line, which represents the half-light radius, you realize an absolutely enormous percentage of the cluster's mass is jammed into a painfully cramped space.
But it isn't just sitting there statically. As you can see, the cluster has contracted so tightly that it mathematically bounced. The energy generated by new binary stars forming in the center essentially halted the collapse and pushed the core back out a bit. It creates this chaotic, central laboratory where stars violently interact on a regular basis.
Which brings us to Section 4, X-rays and stellar vampires, the chaotic reality.
So what actually happens when you squish billions of years of stellar evolution into such a hyperactive space? Well, you get some extreme physics. Joint observations from Hubble and Chandra reveal that this high encounter rate breeds incredibly unusual binary systems. We're talking quiescent low-mass X-ray binaries, active binaries, millisecond pulsars, and a massive population of faint X-ray sources driven by objects known as cataclysmic variables.
Now, a huge feature of this collapsed core is the overwhelming presence of these cataclysmic variables, or CVs. You can basically think of them as stellar vampires. No, seriously. In this cramped environment, two stars get gravitationally locked, and a dense white dwarf literally starts feeding off its neighboring companion star, pulling matter onto itself and blasting out bursts of light and X-rays while it feasts.
And how do astronomers actually hunt these vampires down? They look for very specific clues. On the left side, we look for double-peaked light curves, meaning the star's brightness fluctuates on a repeating cycle of just 3 to 5 hours as they orbit each other. On the right, by looking for excess ultraviolet light and glowing hydrogen gas, known as H-alpha emission, these vampires literally pop right out from the background stars.
Interestingly, they have a sort of split living situation. When we map them out, we see a fascinating bimodal distribution. The bright, newly formed vampires are jammed right in the cluster center where the dynamic interactions are at their peak. But the older, fainter ones? They've scattered outward over time, migrating away from the core as they age and hit their absolute closest possible orbit with their companion.
But here's the twist. Despite hosting all these vampire stars, Caldwell 93 is actually heavily deficient in X-ray sources relative to its incredible density. Why? Well, it turns out the core environment is so violent and the stellar crashes are so frequent that many binary systems are physically ripped apart or ejected before they can even become stable X-ray emitters. It's just wild in there.
All right, Section 5, a gamma-ray mystery, the Fermi telescope discoveries. It's not just X-rays and visible light leaking out of this core. There's an even more energetic puzzle at play. Using data from the Fermi Gamma-Ray Space Telescope, Caldwell 93 was recently discovered to be spitting out gamma rays. And since millisecond pulsars are the only known steady gamma-ray sources in these globular clusters, this high-energy emission is absolute proof that rapidly spinning, highly magnetized dead stars are hiding inside.
But the plot thickens. The data shows these gamma rays are sometimes coming from completely offset from the exact core. This is a brand new mystery for astrophysicists. If the heaviest objects are supposed to sink to the center, how are these incredibly dense pulsars migrating outward within the cluster's tidal radius? It actually suggests that the dynamical bouncing of the core we talked about is literally kicking these pulsars around like billiard balls.
Finally, Section 6, the future of Caldwell 93, looking ahead.
So what is next for the Great Peacock Cluster? Well, the future of studying this ancient relic relies on our newest, most powerful tools. Scheduled Cycle 1 observations with the James Webb Space Telescope are going to peer directly into this cluster to finally hunt down elusive brown dwarfs. Because brown dwarfs just continually cool over the entire lifetime of the cluster, finding them will let us push and test our stellar models completely past the hydrogen burning limit.
Which leaves us with a really fun question to end this explainer on. If we've already uncovered fast-rotating ancient stars, stellar vampires tearing each other apart, and gamma-ray-spitting pulsars playing billiards inside this supposedly quiet 12.5 billion-year-old cluster, what completely new extreme physics is JWST going to illuminate in the darkest corners of Caldwell 93? Thanks so much for watching, and I'll see you in the next one.